Welcome to Fundamentals of Distillation Operation. This video will guide you through a virtual distillation plant where crude oil is separated into several refined products. The basics of distillation are explained by covering each component in the plant step by step. After this introduction, we'll look inside a distillation tower, view how separation is established, see how gas and liquid flow through the tower, and discuss common issues resulting from incorrect operation or damaged equipment. Let's remove all components surrounding the distillation column. Distillation is the most common separation technology used in petroleum refineries. The separation of substances is accomplished by making use of the differences in volatility. The liquid mixture is separated into fractions through partial vaporization and the recovery of the vapors and residue. The distillation towers have liquid outlets at intervals up the column which allow for the withdrawal of fractions that have a specific boiling point or boiling range. The lightest products exit from the top of the column. The heaviest products exit from the bottom. Products exiting from the top have a lower boiling point than those exiting from the bottom. The process is operated at a continuous steady state. New feed is constantly added as products are withdrawn. The feed is preheated, in this case by a furnace. The heat vaporizes the volatile components, and the vapor and liquid are fed into the column. The liquids will pass down the column into the stripping section, while hot vapors pass up the column, which is referred to as the rectifying section. Inside the column, a series of trays force contact between the vapor and the liquid. To maintain the appropriate temperature in the column, the necessary heat is supplied by a furnace reboiler. Part of the bottom product is pumped into a furnace and fed back into the column. Reboilers generate the vapor to drive the fractional distillation, and therefore proper reboiler operation is vital to effective distillation. This picture shows how the furnaces and the column we discussed are represented in a diagram. Steam stripping may be required for compounds that will decompose at sustained high temperatures. Because normal distillation will not work effectively, steam is added. The addition of superheated stripping steam lowers the hydrocarbon partial pressure in the tower. This lowers the boiling point of the compound. Therefore, steam stripping will allow a fraction to evaporate at a lower temperature, avoiding the decomposition resulting from normal furnace reboiler operation. Here we see a high-pressure steam stripping sparger that is used to distribute the steam into the column. The pipes have small holes acting as orifices to maintain the appropriate pressure. It is important that the superheated steam is completely dry and doesn't contain any condensed wet elements. By routing the steam through a knockout drum, the wet steam can be collected as it condenses in the drum. The dry steam can now safely be added to the column. Lighter products exiting from the top of the column are recovered by letting them cool in the overhead section. Vapors are condensed into a liquid. In this case, the heat exchange is established by air cooling using a series of fans. The hot product moves through a series of pipes while these fans blow air from the bottom. The latent heat is given up by the product and will transfer to the air. Gaseous substances will condense to their liquid state, and the liquid is then recovered into a reflux drum. The liquid is further allowed to cool off in the reflux drum. At the bottom of the reflux drum, a boot is collecting water. As water is heavier than oil, it will sink to the bottom of the reflux drum and can be purged from the system. Part of the condensed portion of the lighter liquid is pumped back into the column. This reflux achieves a more complete separation of products. Inside the tower, the downflowing reflux liquid provides cooling and condensation of the upflowing vapors. Reflux improves the separation process and therefore the quality of the product and efficiency of the tower. In general, the more reflux provided, the better the separation of lower boiling materials from higher boiling materials. However, the amount of reflux that can be used is limited. The process of separation is driven by the liquid-vapor interaction, and if this is out of balance, efficiency can be lost. Further, since reflux introduces liquid that has been allowed to cool down, the reboiler needs to work harder to compensate. In other words, increasing reflux can increase costs of operation. Here we see another thing that can happen when excessive reflux is used. The spray headers introduce so much liquid that it starts to form a barrier for the vapor flow. The vapors can't escape to the top and flooding results. In some units, undesired elements could make their way to the side draw. For example, the H2S shown here should escape in its gaseous state from the top of the tower. From there, it would be processed in the gas recovery unit and ultimately in a sulfur plant. However, in the situation where the flow of vapor is blocked, the elements could show up in the side draws. This is highly undesirable and should be avoided. The H2S in this case is used as an example. Each feed is different and will have unique properties to consider. Water collected at the reflux drum needs to be properly drained. If it is not properly removed from the pump-around system, the cold water entering back into the column can have disastrous results. Cold water will expand about 1,600 times when making contact with hot oil. The expansion will create an enormous pressure increase that can severely damage the tower internals.